It says it's starting. And we're live. Great. Fantastic. So, hello everyone. Welcome to our first virtual astronomy on tap meeting. And since we couldn't go to the bar, or the astronomy rather, came to you, directly to your screen. So first of all, let's really quick introduce ourselves. My name is Asha. I'm a PhD student studying Galaxies in Cambridge. And off to you, Annabelle.
Hi, I'm Annabelle. I'm a first-year PhD student at Cambridge too. I'm studying AGN feedback, so black holes in clusters of galaxies.
Haley?
I'm Haley. I'm a postdoctoral researcher in the maths department in the University of Cambridge, and I work in cosmology and general relativity.
Thanks. Johnny?
Hi, I'm Johnny. I'm a first-year PhD student at the Institute of Astronomy here in Cambridge, and I study planetary atmospheres.
Thanks. And now to the star. Not the start, but the star of our show, Gareth. Tell us a couple of words about yourself, please.
I'm Gareth Jones. I'm a postdoctoral research associate at the Kavli Institute in Cambridge, and I mainly look at really far away galaxies and figure out how they move and what they're made of.
Thank you. So before we begin with Gareth's awesome talk, let's have a couple of bookkeeping things aligned. So first of all, we will not be answering your questions in the live YouTube chat. In order to interact with us, we've set up a Slido event, which you can access at slido.com using event code capital A-O, capital T, AoT. In the Slido app, you can both ask the questions and then participate in our quiz, the game that we prepared for you after the question and answer session with Gareth. So if you would like to take active part in interacting with us, then please go ahead, go to slido.com and log in under hashtag AOT, capital A, small o, capital T. Great. So on that note, let's just let's start off with Gareth's talk.
Alrighty, so I will share it there. Cool, so yeah, I'm pretty excited today to be able to tell you about the radio universe, especially looking at galaxies. So first of all, when we talk about looking at the radio universe, we're not looking at radio sets floating around in space. There's probably one or two of them, but we're not trying to observe them. We're looking at things in space that emit radio waves. So just to talk about what radio waves actually are. So light has a whole bunch of different wavelengths and different energies. And if you start off on the really high energy side, you have gamma rays and X-rays. Then moving down in energy, you have ultraviolet, which is what gives you sunburns. You have visible light, which is what you see, all the way red through purple. Then going down even more, you have infrared, and then microwave and radio. But the strange thing is that pretty much everything, all light with a wavelength below a millimeter can be called radio, or millimeter or submillimeter or microwave. There's a whole bunch of different names, but the main thing is radio waves are light. So the same sort of thing as gamma rays or visible light, but just with much lower energy. And I actually had to look this up because I was curious. Microwave ovens emit light at 12 centimeters. So technically they're centiwave ovens or radio ovens. That's just a side note. Yeah, radio waves are low energy. And when we want to look at these in space, we don't just use regular telescopes like you would have in your backyard. We use a bunch of different ones. So here's a little pop quiz. These are 7 objects. You can try and guess which of these is not a radio telescope. Give you a second to look. If you guessed D, that's actually the FAST antenna in China, even though it looks like a giant metal crater. This is a functioning radio telescope. E is the Parkes antenna in Australia. G, that big one, is 26 West, and that little smiley face guy is actually a real telescope that's called Smiley. B, even though it kind of looks like a very poorly designed bathtub, it's actually part of the Paper Array in South Africa. That's also a radio telescope. F is a very badly designed tent, but that's part of the Long Wavelength Array. And then if you had guessed A or C, then I wouldn't have blamed you for thinking those were not telescopes, but those are both part of the LOFAR array, which is spread across Europe. So the answer here is that all of these things are radio telescopes, and there's hundreds more spread across the world. But yeah, radio telescopes, they come in different sizes, and they have a bunch of different shapes, everything from wires to giant dishes. I didn't point out, but this Parkes antenna is sitting on top of a 3-story house. So that gives you a sense of scale. All right. And you may think that some of these are kind of strange, but you might actually be more familiar with these antennas than you might think. So 2 of the most famous ones are the Very Large Array in New Mexico and the Arecibo dish in Puerto Rico. And if you watch the movie Contact, this Very Large Array is the instrument that Jodie Foster used to listen to aliens. But if you did watch the movie, I should point out that radio astronomers don't usually drive out into the middle of the array and listen to the radio signals on their headphones. Usually we just download the data at our offices and look at the images. And in Arecibo, this was the evil satellite facility in Cuba that James Bond had to go and stop the bad guys at. But I think Hollywood has something against radio telescopes, because in GoldenEye, they blow up Arecibo, and in Terminator Salvation, they blow up the Very Large Array, even though the Very Large Array is much bigger than it should be. I don't know. But thankfully, no telescopes were harmed in the making of these films in real life. Okay, so we know what radio waves are. We know what radio telescopes are. So now what can we actually see with these? So this is a bunch of different images of the center of our galaxy, the Milky Way, at different wavelengths, with highest energy at the bottom and lowest energy at the top. So starting at the bottom, we have gamma rays and X-rays, and these show you hot gas. So gamma rays mainly come from the very center of our galaxy, where there's a bunch of concentrated hot gas, while X-rays come from the more diffuse hot gas. Moving up into the optical, we see emission from stars like our own, like the sun. Although you do see that there's these big black dark splotches that are blocking the light. And these splotches are actually something called dust. But this is not the dust that you would find on the side of the road or in your backyard. This is actually just everything that's not hydrogen or helium. So it's the byproducts of fusion in stars. So when stars explode, they spread a bunch of dust into the areas around them. If we move to lower energy in the infrared, we're seeing emission from warm dust. So the same stuff that's blocking optical light is emitting light at lower energies. And then if we move up to the upper 4, we're looking at cool gas, which is the stuff that collapses together to make stars. And for the rest of the talk, we're just going to be kind of focusing on all of these radio waves here and looking at the cool gas in galaxies. Before I move on, it's just kind of cool, because if you want to study the life of a star, for example, you can look at the cool gas that stars are made of. And then if you're looking at newborn stars, they're radiating at a really high rate. They're really hot. So they're visible in the X-ray and gamma ray. As they kind of cool down, you can see them in optical. And then once they explode, you can actually see their byproducts in infrared. So if you look at different wavelengths, different energies, you can see different parts of the stellar cycle. And there's a whole bunch of cool synergies if you observe the universe in multiple ways at multiple frequencies. Right, so just another comparison of what we see at different wavelengths. So these are both images of the Whirlpool galaxy, and on the left is optical. In the white, you can see normal stars like our sun. On the red, these are newborn stars, which are really bright and really hot. And then these brown regions are the dust that's blocking the light. And you can see 2 really nice spiral arms and a really bright center. And then if we move to radio, and we're looking at cold gas, the stuff stars are made of, that traces the spiral arms really well, and it's pretty much right on top of all this dust. And we can see that the radio isn't blocked by the dust, where optical can't get out when there's dust around. So we can see that these spiral arms are places where stars are being born. It's pretty neat. So there's hundreds of observations of galaxies in radio. This is just one really nice mosaic from a really big survey that was done a little bit over a decade ago. So in the center, we have our galaxy, the Milky Way, and this is an artist's rendition of what the stars should look like, because we can't actually get outside of our galaxy to look at what our galaxy looks like. And then on the left is our actual gas distribution, so our star formation fuel in our galaxy. And then around this in a spiral is the gas in other galaxies that are near us at the same scale. So we have some that are smaller, some that are much bigger. Some have like a really compact disk with a big diffuse cloud halo around it. Some have a really bright center with no dust around the center. There's just a whole bunch of shapes and sizes and different inclinations and all that. So yeah, pretty neat. Yeah, so those are all local galaxies. But if we look at faraway galaxies, we can actually do a little bit of time travel. And to illustrate this, just to bring you up to speed on the history of the universe in 30 seconds. So the Big Bang happened. Everything was really dark until the first stars formed. These stars started coming together into the first galaxies, which then collided and evolved over the next 12 billion years to the present day. So if we look at galaxies near us, like Andromeda here, where the blue is the gas, we can see galaxies at amazing resolution. We can see the spiral arms, we can see the central regions, we can tell there's dust, there's gas, there's stars. But the crazy thing is that these galaxies are, I think in this case, it's like 2 million light years away, which means the light's been traveling for 2 million years. So we're seeing this galaxy as it was 2 million years ago in the past. And we can do this trick for much farther away galaxies. So this is another one that's around 3 billion light years away. So we're seeing it as it was 3 billion years ago. And the universe around it, in which it's situated, we're seeing it as that was when it was only 10.5 billion years old. Because I forgot to mention, the universe now is 13.8 billion years, but we can look at earlier baby pictures of the universe. So moving back farther in time, we could look at, this is a galaxy that's around 10 billion light years away. So we can see it as it was when the universe was only 3 billion years old. We can do another one where the universe is only 600 million years old. And then the current record holder is a galaxy called GNZ 11. And this is 13.4 billion light years away. And we see it in a universe that's only 400 million years old. So this is one of the first galaxies. And it's definitely time travel. So you might be thinking that all of these images look pretty terrible compared to picture of Andromeda and all the pictures that I've shown up until now. And to illustrate why this is, I'm gonna play a quick video and hope that the FPS works. So this is going to show a zoom in on the sky around GNZ 11, and it'll hopefully give you a view as to why everything's so pixelated. But first, this is the Big Dipper, and in case you were lucky enough to see Neowise, that's right over there. So yeah, this is going to zoom. Oops, sorry. No, there we go. So it's going to zoom in. It's going to show the Big Dipper, and then as part of Ursa Major, it's going to show a picture of a bear that I think looks like a wombat, but that's fine. So these are a bunch of optical images, I think, from Hubble, and all of these points are stars or galaxies, and it's going to keep on zooming in, and in. You're going to see a red dot right about now. And that tiny itsy bitsy red dot is the farthest away galaxy that we've seen, GNZ 11. And the fact that it's not just a single pixel, but we can actually see some strange extended blobbiness, that's something that's 13 billion light years away is insane. So I'm just going to play this again because it's kind of pretty, and then talk about what. So this galaxy is 1 arcsecond wide. So in order to picture what that is, imagine looking at a computer screen in London while you're sitting in Cambridge, or holding out a piece of hair at arm's length and then dividing that width by 10. So these are tiny, tiny galaxies. So the reason all these images look so terrible is that they're itsy bitsy, and the fact that we can see them at all is only possible with current telescopes. Pretty pictures. All right, so since our images right now are kind of iffy, what we need to do is compare what we see with what we expect to see. We do this by looking at simulations of galaxies. So this is a simulation of a galaxy where the different colors are how much gas we see. So the light blue shows really diffuse gas, while the red and yellow shows a lot of gas. So this is different scales. So just starting on the right here, we see this yellow disk of gas in this galaxy that's looks pretty well ordered. It has some streams of gas around it. So it's a little bit messy. It's, this gas is falling into the galaxy. These clumps might be falling in, and it's going to be growing as all of this stuff falls into it. But this doesn't look too complicated on this scale. If we zoom out a bit, we see that this galaxy is actually in this long tube of gas. And not only are there little clumps near the galaxy, there's clumps all over the place. And if we zoom out even more, it gets even more complicated because this column, this filament of gas, is really long. It has a whole bunch of galaxies in it, a whole bunch of clumps. So the situation is really complex, and doesn't really help that the images that we're seeing right now at the same scale as this kind of look like that. So the background is an infrared view, and these contours here show that there's a lot of radio emission from one galaxy over there. So yeah, we definitely cannot see these little clumps, and because they're just not bright enough, and we need much higher sensitivity. We need more time on source to actually expose our cameras and see these diffuse and dim objects. So just another simulation here. So this is showing a galaxy with a bunch of clumps falling into it, sort of in the same situation. And it's evolving with time from the upper left to the right and continuing on the next row. We can see that this is not just a single galaxy that's rotating. It's got all these complex arms and all these clumps falling into it, and it's throwing off these big arcs. And there's merges with a pretty big galaxy over here, and then it gets really disturbed, and then it relaxes into another kind of nice disk, and then it gets bigger. And the thing is that this is actually a 3D process, and we're only looking at this in 2 dimensions. So this is really complex, and we need a lot more observations to actually figure out what's going on. And yeah, for comparison again, at the same scale, this is what our images look like. So simulation, observation, there's a bit of a gap between those two. Yeah, so that's what I have. So just some quick takeaways. So yeah, radio light is just really low energy light. It's not sound waves. Radio telescopes are a whole bunch of things. Sometimes they're big dishes, sometimes they're wires, sometimes they're these weird tents. And then this radio emission, when it comes from space, it's mainly coming from the cold gas in galaxies, which is the stuff that makes up stars. And then if we observe this cold gas from galaxies that are really far away, we can do a bit of time travel and see them as they were millions or billions of years ago. So thanks for listening.
All right. Thanks a lot for a wonderful talk, Gareth. So at this point, I think it is only fair to start taking questions. So in order to do that, let me real quick change the scene. There we go. So Gareth, if I can ask you to stop sharing the screen, that we can have you here. Fantastic. So I will read the questions off to you, and then you can begin by answering them. So the first question, which got the most upvotes, is from Bella. Why are radio images so colorful?
So that's a good question. Yeah, so there's a lot of ways that you can display the data. So if you take a picture of a galaxy in optical light, then the stuff that comes from the red wavelengths, you'll display as red, stuff that looks green as green, stuff that's blue as blue. But with radio waves, they don't have a direct mapping to visible light. So there's no portion of the spectrum that's red. There's no portion that's blue or anything. So yeah, we can display them with a whole bunch of different color maps. We can have, red, green, blue. We can have yellow, orange, red. We can have, different rainbows. There's at least 4 different commonly used rainbow color schemes. And then there's blues and greens, forests, there's everything. So it's to make it pretty is the short answer.
Short, but a good punchline. All right, here comes the next question from someone called the Kitten Lover. So approximately how many galaxies that we know of are there in space?
Oh, wow, that is a good question. So there are surveys now. So people looking at a whole bunch of galaxies where they're finding at least tens of millions. I looked at a survey this morning that was tens of thousands. So I would think, I'm not quite sure, but I'm on the order of, you know, hundreds of millions.
Thanks.
A lot.
Yeah, the ones that we can observe, right? You mean the ones that actually we've cataloged, because there are many that we wouldn't observe, right?
Yeah.
Awesome. Okay, the next question, again from Bella, got most upvotes. Is it important to take a radio image? If yes, why?
Yeah, so looking at radio and images of galaxies is really nice because you can tell, if you look at an optical image of a galaxy that has a whole bunch of dust, in a lot of cases, you just won't see anything. And if you look at X-rays, you might just see the very center. If you look at UV, that's going to be blocked by the dust as well. So radio lets us look at these really dusty objects and actually see, you know, what's there. And even in the objects that we can see in optical and X-ray and UV, these radio images tell us different things, like how much gas is in there instead of how many stars. And also it helps us look for the supermassive black holes at the center in some cases. So it tells us different information and lets us see galaxies that we may not have seen otherwise.
Thanks, Gareth. The next question comes from Tina, and it is, what's the most common type of galaxy?
Right, so I'm not sure about that one either. I would say one that's, I was about to say one that's average size, but that doesn't really help at all. Kind of like I think spirals are the most, or not. I mean, the thing is that like most galaxies are just, if you just define a galaxy as a bunch of gas, then I think the most common would be kind of small, just blobs of gas. But the ones that we see the most are probably slightly larger ones that have some sort of rotation, and they may not have spiral arms, but they have you know, some sort of pattern to them.
Yeah, I think the question is very tricky because you can also ask at which epoch in the universe we're also looking, right? Because if we observe the local universe, it's mostly galaxies that do not have the spiral arms. They look like giant balls of light, blobs. But if you go further and further back in time, then you will see, well, first a bit more organized structures, and then you go back into those beautiful blobby things that you were showing us that maybe they have the underlying structure, but we do not have the resolution to learn about it yet. So I think it's a very tricky question to answer. But I think I've got an easier one that has just come up for you from a person called I Love Astronomy, which is, how hot is the warm dust you observed?
That's a good question too. So this warm dust, for the far away galaxies, it's something like 70 Kelvin. So that's minus 200-ish Celsius. So it's you know, pretty cold for humans, but compared to space, which is, you know, minus 270, it's pretty hot.
Yeah, I wanted to say, you said minus 200 degrees and you called it hot, but yeah, of course, for space, it's pretty hot. Now we've got the next question coming from Richard, and I think it's a very cool one. You will like that. Will you ever get to name a galaxy you discover? And if so, or even if not, what would you call it?
That's a good question. I know a couple Richards too, so that's a good name. But so a lot of people, or a lot of groups, are naming galaxies after the last names of the people attached to it. So there's one called like WMH5 and CLM1. And then there's like a CR7, which is Cosmos Redshift 7, which is a silly name. But yeah, I definitely would not name one like Gary 3, Pretorius 2. I don't know. Probably, yeah, it would probably have a J somewhere in the name, but beyond that, I don't know.
Or would you dare call it something funny like sprinkles or cupcake?
Oh, yeah, maybe. I mean, that would definitely get the paper read. So get a press release out of that. astronomer discovers cupcakes in the early universe.
Yeah, I think that would sell well. Right. Since we've got a couple more minutes for questions, if you don't mind, of course, Gareth. They are still coming in through Slido. So we've got another one from Rachel. How recent is using 3D computer simulations of expected galaxies?
Good question too. So there's been a few of these like really large scale simulations that have come out in the past decade-ish that people are comparing the results to. But I think using like any simulations, there's work in the 70s that people were just putting a bunch of point sources into space and putting them in motion and then seeing how galaxies collided. And so yeah, around 50 years. I mean, it's as soon as computers were made, they started simulating, basically.
Thanks. Thank you. We've got another pretty technical and futuristic question, which comes from David. How much earlier than the current earliest image do you think we can get to see?
Yeah, so there's some really interesting work going on now, trying to get at galaxies that are more than that, like 13.4 billion light years away. And there's so it goes up to, so I'm trying to figure out what the ages are. So the thing is that we get these distances by looking at emission lines that have a specific frequency and trying to figure out what the, or how much they're shifted due to the galaxy moving away due to the cosmological expansion, which doesn't answer that. So yeah, we're looking at a galaxy right now that's in the first 400 million years of the universe. And we think that the first galaxies formed maybe 100 or 200 years after the Big Bang. So I think maybe 200 million, so 13.6 billion light years away, possibly.
These are some insane numbers, I must say, for someone thinking locally. So I think, if you don't mind, Gareth, if you don't mind taking two more questions, I think they're pretty quick. That would be great. The first one comes from Dangerous Attacks. I'm sorry, I love the nickname. And the question is, how cold is it in space?
That's a good question too. So the temperature in space is kind of mediated by the radiation that's everywhere just from the Big Bang, the cosmic microwave background. And so around us, it's like 3 Kelvin. But as you look at faraway galaxies that are in an earlier universe, there's been less time for that radiation to disperse, and so it's hotter. So if you look at something that's 13 billion light years away, then space is like 15 Kelvin. So that's 12 degrees Celsius hotter than that. So it's cold.
So are you saying that if you look further away in space, not only are you looking back in time, but you're also looking towards a hotter universe, looking up in temperature?
Yeah, it's true. Yeah.
Pretty awesome. Okay, now the final question, which is actually a combination of two questions from Dangerous Attacks and Talian Time. And the questions are, why are the pictures of some galaxies so blurry, pixelated?
Yeah, so the thing is that for a lot of these images, it's just the way that we're creating pixels. And so we can kind of average these pixels and just have like one big value for the entire galaxy, or we can make the pixels smaller. But as we make them smaller, the noise in the image increases. And so it's kind of a balance between actually being able to see anything and being able to tell what's there. And so when they're really pixelated, that means that whatever's in the middle is pretty dim for the most part.
I see. Thank you. So at this point, I think we've used up your question time. So we're not going to ask Gareth any more questions. However, if if you still would like to ask a question, and if we have time at the end of the event, please keep on posting them on Slido. Maybe we can return to them after we're done with the quiz. Now, at this point, we would like to move towards the quiz, so I'll give everybody 2 or 3 minutes of a rebreather before we move on, and switch. Switch to the quiz mode, and as I've said, in 2 minutes' time, we will reconvene to take a look at the quiz. In case you didn't have a chance to join Slido yet, please go to slido.com and put in the hashtag AoT for the event code name. That's where you can access both your questions and the quiz that I am going to launch very, very soon. Since it is it is an AoT meeting, I do have an equivalent glass. It was filled with apple juice, however, but you can't do much about a time zone. And Gareth, you are...
In the meantime, Asha, can
yes?
I just jump in? I think we do have a question on Slido, which has a question part to it, but also has a very important part that I think we should say something during the break. So we have a question from Allsops, which might be answered later, but I'll ignore the science part. Allsops also wants us to give a special birthday shout out to Jack, who is 12 today. So to Jack out there, I just want to give you a very happy birthday from the Astronomy on Tap team. And I hope you've had an absolutely fabulous day and have ended it with some science today. So back to you, Asha. I just thought that was too important to hold off on.
No, that's fantastic. Thanks a lot for chiming in, Hayley.
Also, we'll get to your question later on. Don't worry about that.
Yep. Yeah, trying to be the technical MCM, pressing all the weird buttons. Okay, I think we can start. So happy birthday, Jack, if I remember correctly, right? Hayley?
Yeah, it was Jack. That's
yes.
right.
Happy birthday, Jack. Sorry. So once again, happy birthday from all of us. Thanks, Hayley. And let's move on with the quiz. We have the quiz is entitled Science or Fiction. And the idea is for us to present you with either a photo, a video, or a fact. And your task is to decide whether a given statement is a piece of science or fiction, a piece of science fiction. So let's get going. If I can only activate that. Yes, I can. The first question is, the image shows science or fiction? We will give you 30 seconds for an answer to each of those questions. And since we have a tiny bit of latency through our YouTube stream, the 30 seconds should be roughly enough to make a decision and catch up with us in real time. So once you've answered the question, we will see how many people answered. And most of you said it's science. And that is indeed correct. The image you've just been shown is an infrared image of an exploding supernova. So as much as it looks like an artist's impression, it actually is a piece of science. Now, the next question is a fact. When we look at the night sky, some of the stars we see may no longer exist. Is that science or is that fiction? Again, if you would like to join the fun, please go to slido.com, enter our event code AoT, and participate in the quiz. Five more seconds. Ooh. I'm really not doing a good job as a game show host. Oh, wow. Everybody answered the science. Yes. Well done. Well done, everyone. That is true. This is because, as Gareth said, the speed of light is finite. So chances are that the light emitted from a faraway object that has been traveling through billions of years to reach us could have been emitted before an object exploded. Great. Now, we've got another image. The question is, again, is it science or is it fiction? Or shall I rather say an artist's impression? That's the jargon we usually use in this particular case.
This is a tricky one because it looks a lot like a bit of a wormhole there, doesn't it?
Yeah,
Mm.
yeah. That's something I would easily imagine seeing in the Guardians of the
Yeah.
Galaxy. Oh, wow. Look at the split, everybody. We've got 55% science and 45% fiction. Well,
Ooh.
yep, that was tricky. So thanks, Haley, for suggesting that. Actually, it is science. So the reason why this image looks so out of this world is because it combines information from different wavelengths, including wavelengths of light that our eyes cannot see. So these images, as Gareth mentioned, so someone actually asked a brilliant question: why are the images of radio galaxies so colorful? Well, it stems from the fact that the radio or X-ray or any non-visible wavelength of light, they do not have a color, and we choose the color in order to represent it. So in this particular image, the scientists decided to make it very, very, I would say, Star Trek-like in colors. Thanks, Haley. That's a very good question. Now, I think we've got a fact. Yes, a fact coming up is when on the moon, you can jump higher than on Earth. Science or fiction?
Well, this depends, right? Because there are some people who can jump pretty bloody high on Earth. So
yeah, but assume that it's you.
On Earth who can jump higher than I could jump on the moon.
yeah, fair point. But let's just say we're the same person, and there was a teleporter, and we could just teleport. Yes, everybody said that this is science, and you're indeed correct. That's because the gravitational field of the moon is smaller, so what we call the gravitational pull in colloquially, which really isn't a pull, but the weight, the resistance against jumping on Earth is higher than on the moon. That's why when you look at those videos from NASA that many people claim, well, some people claim are hoaxed, the astronauts jump like bunnies, which is hilarious. So the next question is actually a video. So in order to launch that, I think that was pretty smooth. Let me play the video for you. And the question is, does the video show science or does it show fiction? And I'm not going to say anything. Perplexed. We've got 10 more seconds, and the reason why I'm also waiting for some additional time is because there is a bit of delay between the stream and us, roughly 8 seconds. So, 10 people managed to answer, and the answers are, wow, 40% science, 60% fiction. Well done, Haley. That was your idea.
Yes.
So
I tricked you guys.
Yep. This is actually science. Haley, can you tell us
yes.
what that is?
Oh gosh, well I can't pronounce the name of this comet.
No, you don't have to pronounce the name of the comet.
Okay, good. It's got a very long, confusing name, but basically this is a comet out in the Kuiper Belt, out near Jupiter. It's like 67P / some long name or something. But this is a tiny little comet that's like 4 kilometers across or something, and it orbits on like once every 7 years. So it's this tiny little thing, but we managed to put something on it. Like we sent a lander out to it and we sent it down and it landed on the Earth, and that's what these images are. So that's from the European Space Agency's Rosetta mission, if you want to look it up. Really, really cool stuff.
Yep. And I must admit that the videos got me at first because I looked at them and thought, this looks like 70s science fiction snow on a comet kind of arrangement.
It's so cool. Yeah. And all like the cosmic rays, I think that's what they are, like dust particles or something, like flying. It's so cool. I love it.
Yeah, that was a great question. And I had fun. I had fun thinking about it.
I shouldn't have told you the answer to start with, and I should have tried to trick you.
Oh, no. I downloaded the videos first and then got tricked by myself. And I got tricked by this one. That's for sure.
Oh, good. Fabulous.
Right. Then we've got a fact coming up, which is when in space, you could move around by throwing objects away from you like Dr. Stone did in the movie Gravity. the reason why I brought up Gravity is because it was a very well acclaimed movie, and it's brilliantly done, of course. And they tried to stick real hard to science. They've done their homework. The question is, did they do their homework in every detail, or did they make things up? 60% science, 40% fiction, according to your answers. And guess what? You guys majorly were correct. Yes, indeed. On Earth, if you're holding a wrench and you throw it in front of you, nothing happens because your shoes are held in place thanks to friction. In space, there is no friction. Let's assume it's vacuum. So if you throw a wrench, the momentum you've given to the wrench, the exact and opposite momentum has to be given to you, thanks to Newton's laws. And because of that, you may indeed travel through space by throwing things. That's exactly how jet engines work. They just throw away a lot of material with a lot of momentum. That's all it is. So very well done on that one. Now, question 7 is an image. And you may recall another big movie that has come up in recent years, and the question is this image a science image, or is that some sort of science fiction? I can't wait for the answers.
Ooh, I know, me too. I'm curious about this one. What's that big movie you were talking about?
Yeah, people didn't get tricked.
So close. You guys are too good.
Yeah, you guys are too good. Yeah, I was hoping someone would say it's The Martian, but no. But then again, it's a very popular image. Let's be honest, right? I mean, the selfie taken by them.
Yeah, for sure. But what I thought when I looked at this photo, I thought it looked like, remember that cartoon movie WALL-E, like the little robot who like cleans up rubbish? I thought it looked like him, so I thought I might trick some people, but didn't happen.
Well, it did trick. It did trick 36% of it. Yeah, yeah. We got you a little bit. All right. So the next one, I believe, is a fact. If I remember correctly, yes. So when in space without a spacesuit, you will die from freezing to death. That's something we occasionally see in popular culture and sometimes in movies or in books. Is that indeed the case? Is that why astronauts primarily wear their spacesuits?
We did hear about just how cold it was in space before.
Yeah, 3 Kelvin that Gareth mentioned is not really hot, I must admit.
Not warm. Probably need to take a sweater.
Ooh, 55 to 45. And ready for the grand reveal? That's fiction!
Oh, damn.
Do you guys know why? Haley, any ideas?
I thought it was really cold in space. You're gonna have to take this one.
Actually, freezing to death will take a long while for you to freeze to death, like you would, for example, while climbing Mount Everest. That's what kills you on Mount Everest if you die of cold. But in space, what happens is, because there is vacuum surrounding you and you do have open cavities in your body, like your nostrils, all the air that is free floating in your system immediately exits it. And without access to oxygen, your brain dies within seconds. Actually, it is estimated that it will take roughly a minute and a half for an astronaut to die from suffocation in space. So that's the thing that kills you. You suffocate. But you also lose your consciousness after 15 seconds of being without a spacesuit. So it's a very quick way to go. You will freeze in the end.
That's what I was going to say. So you would freeze to death, but the other stuff will just get you first.
Yes. So yeah, you do freeze. That's true. But it's more like, let's call them space embalming, space preservation.
But at least you'd have a really nice view for 15 seconds before you fell unconscious, right?
Yes, that's true. That's true. Oh, wait. I forgot to say that any exposed liquid on your body, again, vapor, no pressure, would start boiling immediately. So I'm really sorry to say, but if your eyeballs were exposed, they they would kind of boil, which is unpleasant, right?
This is turning quite morbid. I must
Yeah, I'm
say.
sorry. I'm sorry. I didn't mean to. The point being, you will freeze, but after you've died.
Moral of the story, I think we've learned from here is don't go to space without a spacesuit.
Yep.
Cool.
Perfect. Thank you for the summary. That's what we needed. Taking me back on the ground. Okay, the next one is a video, so I need to do a bit of my technical magic. Whoa! Yes. So I'll play a video. I did play the video for a second. Okay, I'll play a video and ask you guys if you think that this video shows science or fiction. That's a good one too.
Yeah, this one's tricky. Well, hopefully. That's the point.
I think we've done some homework on tricky questions. Well, we tried.
This one kind of looks like some little bacterium or something, I thought.
Yeah, or amoeba is
Amoeba. All right, let's get technical.
Oh, sorry. And the results are in, so let me close it. And wow, a great majority of you said it was science. Oh no. Sorry, that's just me. Yes.
Whoops.
Yes, fixed it. And yes, you are correct. Actually, this video comes from a simulation. It's a real simulation of an exploding supernova. But the reason why it looks so weird is because it's the initial stages of the explosion. Correct, Haley?
Yes, that's right. This is just the first very, very short part of this movie. It does go for longer. And you get this big, like, weird shaped cloud that's hot in different places and cold in different places. It's very cool. If you Google supernova explosion simulation, you'll find some cool stuff. So check it out.
Yep. I strongly recommend following Haley's advice. Now, we've got question 10. If you saw a spaceship explode, you would hear the explosion like we do with example exploding Death Star in Star Wars. It's one of my favorite movie scenes ever. So I'm very, very partial to this question. I think it's no secret I came up with this.
Don't give it away, Asha.
No, I'm not giving it away. I'm just saying it's my favorite movie. My favorite scene. Oh wow! All of you said it's fiction.
Guys.
Yeah, and of course you know why this is fiction, but I still feel for educational purposes, I still feel obliged to say that you cannot hear sound in space because sound waves need a medium to propagate. So we would see the light, and that would be just a silent fireworks show. That's all it would be. But the sounds are needed in order for us to watch the movie with pleasure. So, let it be.
Yeah, it wouldn't really have the same effect, would it?
No, it surely wouldn't. In the meantime, I managed to switch to another image, which might be either science or fiction, and you are to decide. And I think, Haley, this one is particularly tricky.
This is kind of a trick question, so I'm really curious to see what you guys think of this one. It's tricky. I don't know.
For those who are familiar with Pancake or Planet or Pan on Planet, you should know that Haley is good at tricking you.
Anyone staying at the pub with us knows that I like to trick you.
Right. So we've got 73% science. Now, the grand reveal. Can I have the drums? I should have drums for this stream. I'll have some sound effects for next time.
Yeah, I'll bring a drum next time.
And this is fiction. Woo! Well done to those of you guys who marked it as fiction. Haley, can you explain where this image comes from?
Yeah, so this is the trick question in it, because I would actually vote that it's science. But so technically it's fiction, right? Because this is Gargantua from Interstellar, which is the supermassive black hole. But it's scientific because there's actually a whole peer-reviewed paper dedicated to this black hole and the way that it looks, because scientists wanted to figure out what would a supermassive black hole actually look like if we would be able to get this close to it. So they made this black hole like a simulation with a disk around it. And this is pretty much almost exactly what it would look like. And the reason it looks like that is because the light is bent around the black hole. So what you're seeing at the top is actually the back of the disk, and what you're seeing at the bottom is like the underside of the disk. So it's really confusing. General relativity does some weird bending of light and stuff, but it's not. So they came up with what the disk looked like, and they didn't quite like it. So they just kind of like amped up the light a little bit to make it a little more like movie-esque. So it's technically not exactly scientifically accurate, but it's pretty damn close, which is cool.
Yeah, I agree. I found that detail also very very satisfying.
Yeah, so everyone wins.
Yeah.
We're all right on that one.
Oh, people managed to change their answers. Look at that.
Oh,
I flipped
no.
the image back.
You could do that.
That's great. That's great. I like that.
That's
like
cool.
that.
I changed your minds.
Yep. No, that's pretty cool. I actually like that a lot. All right. So the next question, I believe, is a fact. Yes. Dust storms on Mars are a threat to future missions because they could damage the equipment as portrayed in the movie Martian. As you know, as you may be aware, there is plenty of efforts across the globe, including some private investments from very wealthy people, trying to go to Mars and, before colonizing it, let's start small, setting up a human base. And there are a lot of challenges associated with setting it up. And the question is, could the dust storms be a real challenge? Now, this is a tricky question because I specifically asked because they could damage the equipment. And the answer is, it's fiction. So dust storms are dangerous to human habitat on Mars because the dust, well, first of all, they're frequent. Second of all, they can reach high speeds and carry a lot of small dust particles. But because the density of atmosphere on Mars is roughly 100 times less than that on Earth, the amount of the momentum of air, atmosphere hitting the equipment is negligible. So a good comparison probably would be if you imagine the atmosphere being water in your hose, and the atmosphere on Earth is the fire hose that firemen have, and the atmosphere on Mars is your garden hose. So if you get hit with a garden hose, not much happens. You get wet, right? But you don't move. But if you were to be hit with a gigantic fireman hose, you would be swept away dead. Well, maybe not swept away dead, but at least bruised a lot.
Back to the morbidness of it.
Sorry.
Always bring it back.
I'm sorry. I didn't mean to. That's I don't know. I really shouldn't be doing live quizzes. Anyway, the point being that dust storms are indeed a challenge, and they are a challenge to rovers. You may have heard of rovers that were losing connection with Earth just because dust storms came over. They're covered their solar panels, and they have to save energy. Some equipment had to be abandoned because of that. But these storms wouldn't dramatically sweep over equipment like they did in the movie Martian, flying pieces, tents being destroyed. No, that wouldn't happen. Now, question number 13 is again a movie, so I'm trying to do the magic real quick, because why not? There we go. And the question being, does the video show science or does it show fiction?
Oh, this is probably one of the coolest movies ever.
Agree. Although when I look at it right now with this blue background, it reminds me very much of, what's the name of the movie that everyone is watching right now as well? Pandemic or something? One of the
Very appropriate.
big Hollywood productions.
Oh, like Contagion or something?
Oh, Contagion, yes. Thank you, Haley. Oh, okay, so we've got 60% science, 40% fiction, and you guys, you didn't get tricked.
Damn it.
This is science. Haley, can you tell us what that is?
This is a really, really cool movie. So what you see here, the blobs that are moving around, are actual stars in the center of our galaxy. So if we just stare directly into the middle of the galaxy, we could see all these stars. And you notice the one in the middle kind of whizzed around really, really fast. but there's nothing there. Like we can't see anything that it's whizzing around, and things always orbit stuff. So what you can do is you can look at this image, and this is actually something I did in my undergraduate astronomy, and you can map out, awesome, thank you. You can map out the paths of the stars, and we can tell how massive they are by their light. And then from that, you can figure out how big the thing must be that they're orbiting for them to move in that way. And doing this, like a really simple calculation, doing this, you get something that's like 1,000,000 times the size of the sun. But if you look at this picture, right, there's nothing there. So it also has to be really physically really small. So the only thing that we know that fits those two criteria is a black hole. So pretty damn cool.
Yep. Direct evidence, if you like, for the existence of black holes.
Yeah.
Now, moving on with the quiz. Actually, before we move on with the quiz, there's a question in the chat from Tom Brown. So the stars just look like that because they are out of focus. Blobby. Is that correct?
Sorry.
Tom Brown asks if the stars look blobby because they are out of focus.
Yeah, it's just because they're really far away. So the fact that we can see, normally when we look at stars, we just see a point of light, but because these ones are much, much closer than stars that we normally look at, we can see that they're extended objects. So yeah, it's the same reason as what Gareth was talking about before, why they're a bit blobby, is just because the resolution's a bit low. Yeah.
Thanks. So we'll move on to the next quiz question. And I will come back to Tom because he has another cool question to you, Hayley. If you would like to chat, you could call your friend who is on the other side of the galaxy. As seen an example, Star Wars. So in the movies, you see that a lot, right? People flipping at their new hologram iPads that consists of a single rod, and they call their family from a different planet. Or they holograph themselves into a council meeting. Is that correct? 100% fiction! Woohoo!
Good job, guys. I'm relieved at that one.
Me too. Although it's a detail that it's just so convenient for the plot that you forget about, right?
Yeah, and to be fair, if they had this scientific fact in Star Wars, it would take a very, very long time for them to have a conversation. So it wouldn't be a very exciting movie.
Yes. And a real quick explanation why this is fiction is because if you're so the fastest a signal can travel in the universe is unfortunately dictated by the speed of light. How sad that is. Which means you can only communicate as fast as the light travels between you and your friend. If your friend is on Earth, there is no problem. We're talking in real time because light is so fast compared to the distances we have on Earth. But if you would like to call someone on the sun, you would have to send your signal. The person would hear your message after 8 minutes, and then you would have to wait another 8 minutes for the signal from this person to come back to you, which means this would be a ridiculously long and painful conversation. 16 minutes between every sentence. I don't think this would be movie-esque. No, for sure not. So we've got 2 more questions left. So let's go on. Oh yeah, I like this question. So space garbage can harm satellites or shuttles, as seen in example the movie Gravity. In
Space garbage. I mean, people are littering enough on Earth, let alone in space.
Right. I've recently been looking at the pollution maps around Earth, and when I mean pollution, I mean the positions of all satellites that are known of.
Oh, that's cool.
Yes, and it's scary to see how densely populated the space already is.
Wow.
Right. So you guys majorly responded that this is science, and you are indeed correct.
Good job.
Yes, because these, in the worst case scenario, we're talking about a head-on collision at 16 kilometers a second. These are extremely high velocities. And although the particles are, these chunks, the space debris or junk, can be quite small, it's still, with such a high velocity, it carries non-negligible momentum. So it can potentially indent spacecrafts. As much as it probably wouldn't hurt a spacecraft because they are prepared for things like that. They do have special shields around the spacecraft. You could hurt, for example, the solar panels. They're much more fragile. So that's an important thing people plan for when planning their missions right now. And one thing, if you think about the movie Gravity, if you remember the scene with Sandra Bullock, Dr. Stone, looks at the space garbage and she sees it coming. So it gives the plot some, the ability for us to feel the tension and be scared. Well, that's impossible. You wouldn't be able to see objects moving at you from a distance faster than a bullet. Yeah, imagine a rifle bullet shot at you from, say, 3 kilometers away. Do you think you could see that?
Oh no, a bullet, get out of the way.
Exactly. So that's the same principle. So that's another thing. Well, that's sad that they didn't account for that in the movie, but it would be hard to explain for the audience, and also it wouldn't give you the tension rising moment. So fair game, movie makers.
We'll
but
forgive them for that one.
Yeah.
Let it slide.
Yeah, let it slide. So we've got the final question coming up. And this is an image.
Ooh, pretty.
Very pretty. Science or fiction?
I don't know. I think we're going to trick them with this one again. This is a tricky one.
I have so many references in my head now. Yeah, I think. Yeah, we're constantly on 8 seconds delay, so the stream is working fine. Ooh, 60% science, 40% fiction.
Ooh, that's a close one. Close call.
So the answer is, it's science. It's inside the neutrino detector, if I pronounce it correctly, Superkamionkande.
Sounds pretty.
Yeah. Yeah, I'm really sorry. So yes, this is indeed the that's what the Superkamionkande detector looks like inside. And on that note, we have finished all the questions in the quiz today. So thanks a lot for that, guys. If you didn't manage to catch up with the first couple of questions and want to check for yourself, you can easily still do the quiz in Slido for your own entertainment. But still, I wanted to ask you, Haley, a question from Tom.
Okay.
Still on the stars that we're orbiting. So let me pull them up again. They are visible on the stream right now. So why are the stars not getting sucked into the black hole?
That's a really good question. The easy answer is they're not orbiting close enough. So if they were on a particular trajectory, then yeah, they would go straight into the black hole. But it's because they've kind of just skimmed the edge of it. So the gravitational pull of the black hole has like tried to pull them in, it's tried to grab them, but it's kind of like, it's like if you were to like spin a coin around one of those like funnel donation things. Is that a thing? Is that just an Australian thing? You know, when you like donate, put a coin in and it spins around.
Yes.
So if you're at a certain distance from it, it'll just kind of whip you around the outside, and eventually they will spiral in if they're not in a stable orbit. But yeah, I mean, the easy answer is they're just not quite close enough to get all the way sucked in.
Tom just said, "Oh, that makes sense." So thank you very much
Awesome.
for the explanation, Haley.
Thanks for the question, Tom.
And you mentioned there were a couple of questions that we should probably answer at the end, right?
Yeah, we had one. We have a few left on Slido, so I can just read them out. Gareth, are you still there?
Yeah.
Yay. Do you want to go, Ash, or do you want? Oh no, they're there. Awesome.
Yes. So, shall I just start with the one on the top?
Yeah. I
Okay,
reckon
cool.
we-
So we've got 3 questions left. So let's quickly go through them, and if you don't mind, Gareth will engage you in answering them. Sorry. What was the largest galaxy ever found, and approximately how many stars did it have?
So I may have been cheating, and I just Googled this a minute ago because I saw it. And yeah, because I wasn't sure, because I thought the largest one was, like 10 times the size of the Milky Way, but it's saying that the largest one is actually 50 times the size of the Milky Way. So that's 1 trillion suns of mass, essentially. But it's also saying that it's like millions of light years across. So that's, that's the size of like entire clusters of galaxies. So I'm not quite.
Is that the ICI?
Sometimes, yes, the ICI 40, I think. Or IC something or other. But it's IC 1101.
Yep. Yeah, I think Matt Bothwell in his Talks for Children series was talking about this galaxy, and I think it's real information. It's just that it's mind-boggling how large it is.
It's insane.
So
I learned something new.
Well, we did learn something new as well. Thanks, Gareth. So we've got 2 questions left. The first one from Allsops. How many galaxies are out there? Also, can you do a birthday? Oh, yeah. We've already did a birthday shout out to Jack, who is 12 today. But you can do that.
Another one. Happy birthday, Jack.
Yeah, happy birthday, Jack.
Yay! Yeah, we really hope you learned a lot. So there is final question from, pardon if I do not pronounce your name correctly, Suhail. How were radio telescopes used to take the first image of a black hole last year?
Yes, this is a really good question too. So there was they had a bunch of different radio telescopes. So there was the Very Large Array in New Mexico. There was a South Pole telescope at the South Pole, or in Antarctica at least. And then there were a few in Europe, I think. And they used a whole bunch of different telescopes, and then they collected the data and used a concept called interferometry. So if you have telescopes that are really far apart, you can combine the data in a way so that you can simulate having a radio dish that's the size of the Earth. And if you do that, then you can see really tiny things. So they combined all of that data, and they looked at radio emission from the center of that galaxy. And because they had such a large baseline or distance between antennae, then they could get really tiny, really high spatial resolution, and they could actually resolve that black hole shadow.
Great. Thanks a lot, Gareth. So let me return to it's just the 3 of us now. So
Well, we did get a last minute question from Allsops again. So we did give another birthday shout out to Jack, but we actually forgot to ask the question that they asked.
Oh, how many galaxies there are in the universe? I think Gareth already answered that.
No, so I said how many galaxies have we observed, but how many galaxies are there is a very subtly different and impossible to answer question. So the thing is that there's a difference between what the universe is and what we actually see. So the observable universe, we see, or we've observed like hundreds of millions of galaxies, but as to what is actually out there, like right now, there's more than hundreds of billions at this point, probably. Some mass, less than like a Google, but way more than hundreds of billions. There's a lot. And then if you want to think of even bigger numbers, just think of how many stars and how many planets, and how many grains of sand on every beach in the universe. It's all big numbers.
Not just Earth, in the universe as well. All the other beaches and which we don't know.
Yep. So on that note, I think since we're all here together right now on Zoom, we would like to say goodbye to everyone. Thanks a lot for joining in, and see you tomorrow.
Yeah, join us tomorrow for more science.
Yay! Bye.
Bye.